All right, how y'all doing? We have another day of material to get through today. Today's Walks and Trees. Before we get started, let me remind you that you do have some written homework due this week. And if you have questions about this written homework, I've got office hours. I don't know why I made that a cue. Office hours tomorrow at 12, Tuesday, over Zoom, and the Zoom link you can find on the website in the course contract. So um, come by if you've got questions about it. All right, let's go ahead and move on. We've seen this definition before, but I want to start with this definition again. A walk in a graph is a sequence of vertices that satisfies the rule that every pair of vertices has an edge between them. So the vertex I and the vertex I plus 1 are adjacent. So we're allowed to repeat vertices in a walk. That's okay. It's just a funny walk. But so B to D, then back to B, then up down to C, and then over to D. That's a walk. This one in this case kind of repeats an edge, goes from B to D, back to B, and then around to D again, but this time going by C. But that's a walk in the graph. A circuit is a walk that starts and ends at the same vertex. So this is a circuit, D to A, to C, to B, to A, back down to C, back over to D. Starts and ends at D. We wander around a little bit, and we hit a circuit, okay? The length of a walk is defined to be the number of steps that you take in the walk, which is one less than the number of vertices. So it's the number of the edges. So in this case, I have 1, 2, 3, 4, 5, 6, 7 vertices, but the length is only 6. I went from D to A, that's 1, then to C, that's 2, up to B is 3, back to A is 4, down to C is 5, and then over to D is 6. And so there are 6 steps that we took in the walk. That's if you think about it that way. So it's always one less than the number of vertices or the same as the number of edges. It is an easy definition, though. It's how long you've been walking. So let's give an example of walks going from A to E of lengths 1, 2, and 3. All right. So the length that is just length 1 goes straight from A to E, A, comma E. A walk of length 2, we have to go somewhere in the middle to get to E. So we need a vertex that touches both of them. F would work. We could go from A to F and then from F to E. And for a walk of length 3, we have to go somewhere else and then to F and then to E. For example, we could go A to C and then C to F and then F to E. Okay. All right. So that would be a walk of length 3. Same graph showed that there is no walk from A to G. So if I look at the things that I can reach from A, I'll start coloring in some edges here. From A, I can reach C, and I can reach E, and I can reach F. Those are where I can get to in one step. So now let's just keep going with C. I can reach C to F and C to E, and I can reach from E to F, but all of the edges from A are used up, all of the edges from C are used up, all of the edges from E are used up, all of the edges from F are used up. There are no more edges, and so when I started from A and started filling in all the edges that I could get to, none of the edges take me to G. And so there is no walk from A to G, because, um, A, C, E, and F are the only other vertices walkable from A. So part 3 says identify the connected components of G. Well, this exercise kind of identified one of them. A, C, E, and F, the part that's highlighted in red, they're all connected together, but I can't reach any of the other vertices from it. On the other hand, the other vertices are all connected together also, and I'll draw them out in blue. And those are connected. And so the connected components are A, C, E, and F, and then B, D, G, and H. This graph is not connected, but it has two separate components. Okay. All right. So here's a proof that being in the same connected component is an equivalence relation on the set of vertices of G. So just as a reminder of what an equivalence relation is, equivalence relation has to be reflexive, has to be symmetric, and it has to be transitive. Okay? So let's start by saying it's just showing it's reflexive. So let V be a vertex in G. Then this is almost trivial to write out. V is a walk from V to V. And so V is in the same component as V because anyway, within the same component. So because we could walk from V to V by just standing at V and not going anywhere. So symmetric is would be a little bit more interesting. Let V and W be vertices in G. And we're going to assume that V and W are in the same connected component. That means there is a walk from V to W with possibly some vertices in the middle. Let's just call them, say, A1, A2, up through AK. Then if we go the other way around, W, AK, down to A1, V is a walk from W to V. And so W and V are in the same component. All right, I'm running out of space here, but let's see if we can fit transitive in over here. let V, W, and X be vertices in G. And we're going to assume V and W are in the same component. And W and X are in the same component. So that means there is a walk from V to W, and then there's a walk from W to X. So there is a walk that starts at V and ends in W. It may take some intermediate steps. And a walk from W to X. And again, it may have some intermediate steps. There you go. So can we come up with a walk from V to X? Sure, we can by just putting these together. Then V all the way up through W, keep going all the way to X is a walk from V to X. And since there's a walk from V to X, V and X are in the same connected component. All right. Took a little bit of writing there, but being in the same component is an equivalence relation on the set of vertices. All right. Some more definitions. A walk that does not repeat any vertices is called a path. And a walk that comes back to the same starting point, and that's the only time that we repeat a vertex, is called a cycle. So cycle is a walk that doesn't repeat any vertices except for the fact that it has to come back to the same starting point. And so that's the only one that's repeated. So paths and cycles are analogous to walks and circles, but they can't repeat vertices along the way. So, okay. So let G be a graph and U and V be vertices in G. If there is a walk from U to V, then there is also a path from U to V. So here's the idea. If I can get from U, and I can get from U to V by maybe repeating some of the vertices along the way. Say, let's call these vertices A, B, C, D, E. And I have a walk that goes from U to A to B to C, back to A, back to B, back to C, up to D. Let's say go over to E first, then up to D, then back down to E, then over to V. I can make a path by trimming out some of the stuff that goes in between. So for example, when I see an A and I see an A later on, what if we cut out the stuff in between the repeated A's? I see an E, I see another E. I can cut out the stuff from the first E to the second E. And that gives me U, A, B, C, E, V. Now, that's not the fastest path because I didn't actually have to go through B, but this is a path. Now, U, A, B, C, E, V doesn't repeat any vertices. So the idea is if we see a vertex repeated, we can keep the first incident and then delete everything up through the second incident of that same vertex. And then just keep doing that until we don't have any more repetitions. Okay? So if we have a walk from U to V, we always have a path from U to V as well. There's never any case where we're forced to repeat a vertex. If we have a connected graph and a cycle inside the connected graph, and U and V are adjacent in that cycle, so that U and V are an edge, if I delete that edge, the graph is still connected because a cycle produces connectivity in both directions. And so I can lose an edge and not lose the property of being connected. So if you were in any of my Friday face-to-face classes, we talked about this proposition indirectly when we worked an example on the board that day. All right. Some definitions. A tree is a connected graph with no cycles. So it has to be connected, but nothing loops to each other. And a leaf in a tree is a vertex that has a degree 1. Okay? If I delete any edge from a tree, so say if I have a tree here, deleting any edge will cause the graph to become disconnected. Then suddenly we have this isolated node here. So I can't delete any edge. This proposition, the proof comes from this theorem here, 1221. The idea is that in a cycle, I can delete an edge and not lose connectivity because I can connect from U to V directly, or I can go around the other direction. If I don't have any cycles, I don't have that redundant connectivity, and so deleting an edge causes the graph to causes the graph to disconnect. So it has to do with the fact that a tree has no cycles. On the other hand, if I delete a leaf from a tree, the rule is when you delete a vertex, you also delete the edge that comes with it. You still have a tree when we do that. Deleting a leaf from a tree results in a graph that's still a tree. So we can't delete an edge, but we can delete a leaf. Okay? Our last definition for today. Yay, last definition. A graph is bipartite if we can identify its vertices into two disjoint sets, x and y, in such a way that every graph edge in the graph connects a vertex in x and a vertex in y. If we think of this informally, the vertices form two teams, and every edge connects a member from one team to a member of the other team. So this is an example of a bipartite graph. Originally, bipartite graphs were found to be useful in talking about electrical phenomena where we were connecting graphs of positive and negative polarity, for example, and we didn't want to connect two vertices of the same type. So every edge connected a positive pole to a negative pole, for example. So we could think of the two teams as being positive and negative. We have found other applications for bipartite as well. But so if we could just color these, red vertices and blue vertices, and be sort of neutral about our context here, what we're doing here. Every vertex connects one type to a different type. We don't have any edges from red vertices to red vertices, and we don't have any edges from blue vertices to blue vertices. Okay? So that's what it means to be bipartite. We have the vertices form two teams, and all of the edges connect something from one team to something from another team. A graph is bipartite if and only if it contains no cycle of odd length. I'm not going to take the time to write a proof of this, but here's the idea. If we have a cycle of odd length, let me switch back to black for a moment, essentially a triangle, when I start to match the teams together, this vertex could be, vertex could be on the red team, and then this vertex could be on the blue team, and then this vertex couldn't be on either team because it connects both to both red and blue. If I have a even cycle, I don't have that problem, because I can make the vertices, I can make every other vertex red, and I can make every other vertex blue. And that's perfectly good. But for an odd cycle, I can't finish the cycle. And so Theorem 1413 says that in order a way of testing to see if a graph is bipartite is just to see if it has any odd cycles in it, triangles or pentagons or heptagons or nonagons or so on and so forth. And if it does, it's not bipartite. Corollary for that, though, is because trees don't have any cycles at all trees are bipartite. And we will do something with that next time, but we are done for now. Y'all take care. See you around.